Hi everyone, welcome to lectures 7 and 8. And in this PowerPoint, we are going to be reviewing in closer detail the RH blood group system, which is chapter 6 in our blood bank textbook. So please, check out the textbook. There are really some great questions at the ends of the chapters that can help you, if you want some practice questions. So let's start out with our objectives today. So we're going to explain how the D antigen was named RH. We will describe the current genetic theory of the inheritance of RH system antigens. We will also discuss the biochemistry of the RH system, including the gene products and antigen structures. And we will compare and contrast genetic theories behind Fisher race, Wiener terminologies, and translate them from one to the other. We will also compare the Rosenfield and International Society of Blood Transfusion ISBT terminologies with the Fisher race and Wiener terminologies and discuss their uses. Predict the RH genotype given a phenotype. Define weak D and list the genetic circumstances that cause this phenotype. Discuss the significance of testing for weak D antigen, and explain the test for the weak D antigen and the importance of an appropriate control. In addition, we will define cis product antigens and give 2 examples of this phenotype, describe the inheritance and significance of the G antigen, explain the significance of RH null, RH mod, and deletion phenotypes, and describe the characteristics of the RH system antibodies, their clinical significance with regard to transfusion and hemolytic disease of the fetus and newborn, which is also referred to as HDFN. So we have quite a lot on our plate today. So let's get started. So history of the RH blood group system. It was discovered or linked to red cells and transfusion in the 1940s, and 2 researchers who were really integral to learning more about the RH blood group system were Levine and Stetson. So they linked the RH system to hemolytic disease of the fetus and newborn. And once we get into module 3, we're going to be getting into a lot of detail about HDFN and when it can arise. But let's just say for now that HDFN due to RH was really serious and resulted in the death and stillbirth of a lot of infants until we learned more about what was going on. So I don't want to get into too much detail of it now, but we're going to be spending a lot of time talking about it later. So somewhat later than the ABO system, okay? So LynnC and Wiener actually found that there was they called it anti-RH, an antibody against RH. And this antibody agglutinated 85% of human red blood cells. And it failed to agglutinate 15% of red blood cells. And this is really the basis of the D antigen. So these early studies, when we look at the D antigen in more detail in a moment, 85% of our population has the D antigen and we consider them Rh positive. 15% of the population lacks the big D antigen and we call them Rh negative. That LynnC, I'll tell you, what would we do without them? So a little bit more about the history. This human antibody, anti-RH, they found was similar to antibodies that were produced in guinea pigs and rabbits when they were exposed to the red cells from the rhesus monkey, okay? And so that RH here is how our RH blood group system got its name. Ironically, both antibodies were later shown to be different, but this RH name stuck. Okay, so the rhesus antibody that was produced by guinea pigs and rabbits was actually something different. It was an antibody directed against a different antigen called LW. So RH has stuck with this blood group system, and we use it today. So a little bit about genetics and biochemistry. The current theory for inheritance says that we humans have two closely linked genes, and the Rh genes are located on chromosome pair number 1. And these two close genes control the expression of all Rh antigens. And so similar to ABO alleles, those of the Rh system are also codominant, which means that you could inherit quite a few of them. One doesn't have dominance over another. Okay, so let's look carefully at these two closely linked genes. So the first one they call RhD gene, and so this is the gene that determines whether an individual has the D antigen on their red cells, whether they're Rh positive or not. And the second gene is called Rh big C big E gene, and this determines the expression of a whole host of other Rh antigens, which include big C, little c, big E, and little e antigens. Okay, so basically these two genes together control the expression of 5 different potential antigens. And so remember, they're codominant. So an individual could have big D, big D, big C, big E, and little e. They could have all 5 potentially, or they could have, less. And we'll get into that in a few minutes. So interestingly enough, as research was being done over the years, it's been proven that these Rh antigens, not just D, but the C's and the E antigens, they actually have a job. And so they've been shown to provide stability and support to the red cell membrane. And so that is what allows our red cells to live that full 120 days. When individuals lack some of these Rh antigens, the red cells do not survive very long. And we'll get into some details about that a little bit later in this lecture. So there were some other genetic theories that were postulated through the years, and we're going to review these because it's very important to understand their relationship to the current theory. So 2 different researchers, Fisher and Race, came together and said that the Rh antigens were actually controlled by 3 closely linked loci. So there was a big D and a little d. What I should point out to you guys is that there is no little d antigen, but people may write it to designate the absence of the big D, and we'll see how that goes a little later. Big C, little c, and big E and little e. Okay, so they said there were 3 separate loci. Wiener, on the other hand, said that there's only one gene locus and that all of the alleles are inherited from this one locus. Okay, so let's compare. So our current theory, here we see chromosome pair number 1. We could see that RhD on one chromosome and then the CE on the other. And so, we're going to get some information from one of our parents and then, information from the other. Okay. The Fisher-Race theory said that there were 3 separate loci, okay, for the D's, the C's, and the E's. And then Wiener said there's only one location, and they came up with a way of designating what alleles were actually being inherited at at this one site. Okay, we're going to spend some time going over this, and it's going to be important for you to understand it because in blood bank people still do refer back to this Wiener classification for designating which Rh antigens are present on reagent red cells and other red cells. So it's going to be important to understand it, even though at first you might say, oh my gosh, this is driving me crazy. All right. So here we see table 6.1 from our textbook that lists common antigens in the Rh blood group. And you can see here the Fisher race terminology. And then over here we see the International Society for Blood Transfusion number. And so one thing I want to point out, this is, worldwide. These ISBT numbers are used. So if you're in a European country or an Asian country or the Middle East or Africa or what have you, this ISBT applies no matter where you are. So what's very important, you're going to see among all of these, you see the 4. Okay, so with this ISBT classification system, 4 refers to the Rh blood group system. So that's why each one of these, have the 4. And so they've listed all of the possible antigens that have been discovered of the Rh blood group system. And so we see the big D is 4001, big C 4002, big E 003, and then we get into little c, which is 004, little e, which is 005. And we're going to learn a little later that there's actually a compound antigen called F when little c and E come together. And you can see so on and so forth, some of these other ones. And so we're going to concentrate on the top 5 because these are the ones that are most relevant to transfusion. And we might talk a little bit about some of these other ones, but they're much more rare. Okay, so let's get into our Fisher race terminology. So each gene expresses an antigen that is given the same letter as the italicized letter of the gene name. So what the heck does that mean? The italicized C gene produces the C antigen. Not too hard, right? As I mentioned before, there is no little d antigen that has been discovered, but for when we're looking at genes that are inherited, little d is sometimes written to indicate the absence of inheriting a big D, okay? The order of the genes is usually written DCE, not in alphabetical, but sometimes people will order them alphabetically as CDE. It really doesn't matter. Okay, now we're going to get into the Wiener terminology. And so when I get to this topic, I usually joke and call it whiner because everybody's usually whining when they hear me talk about it until you get it. Be patient with yourself. Once you get the pattern, it's really not difficult. But when you look at this slide initially, you might say, oh my gosh, this looks crazy. But trust me, once you get it, it's not so bad. So with Wiener, there are 8 alleles that exist at the single Rh gene locus, okay? And so here are their designations. And so we could see that the first 4 have an uppercase capital R with them. When you see an uppercase capital R, that means that whatever this is has big D antigen, okay? So all of these have big D antigen, okay? Then we have 4 alleles which are small r, lowercase r. And so when you see the smaller lowercase r, big D is not there. So it's, designating that little d is there, but remember little d means that there's no big D. Okay, there is no little d antigen, which in and of itself is a little confusing. Okay, then we see that each one of these letters has, or most of them, have a superscript, okay, something here. And this is telling us which other antigens of the Rh system are present. So let's look at the superscripts and then we'll do some examples, okay? And so when we're looking at all of these, okay, all of these superscripts refer to a capital letter gene like big C or big E being present, okay? So that they mean only capital letter alleles. So when we look at the first one, big RO, this one, think 0. So the only capital letter in the 3 alleles is the D, okay? So RO, let me annotate. RO would be big D only, and then we fill in with small case letters, okay? Because the big D is the only big one it has, okay? When you see a 1 or a prime, you're going to notice that the 1 is used with the big R's and the prime is used with the little r's. This is telling us that big C only is present. So let's look at this one. Remember, the big R tells us they have big D. The 1 tells us that they also have big C, and I remember it because C comes before E in the alphabet. And then we fill in with a little e. Okay, so you fill in with smaller case for the ones that you don't have a capital letter of. Okay, and so we would be getting, you know, one set of these from each parent. Okay, because we get 3 alleles, okay, from one parent. When you see a number 2 or a double prime, this means big E is the only capital one. And when I'm saying that, I'm referring to between C and E, the big C and the big E. Okay? So whenever you see big R, you want to say there's a big D. The 2 means there's a big E. Is there a big C? No. Okay, so we have to fill in with a little c. Okay, because 2 means there's only a big E, there's no big C. When you see the superscript of Z or Y, these are times when both big Z and big E alleles are present together. Okay, so remember, the big R means there's a big D, and the Z is telling us we have both big C and big E. All right, hopefully that makes sense. Okay, so I'm just going to draw a little line here to separate from our smaller case ones. Okay, so let's look at our smaller case ones. Okay, so remember, whenever you see little r, there is no big D. Okay, so I can initially put a little d here. Okay, when you see this little r here and there's no superscript, it means there are no capital C or E. So I fill in with this. Okay. Oh boy, that looks bad. Let me try. It's really hard to, let me just erase that one. It's kind of, okay. Let me go back. Maybe I'll go to a different color. Okay. I want to go to, sorry guys, you got to bear with me. I want to go to my pen again. I want the eraser. Oh, silly. Let's start over. Okay. So I didn't write it well the first time, but it's going to be big D, little c, and little e. Okay. It still looks bad. Okay. All right. Let's look at the R. Let's look at this one. I'll do an arrow down here. Give us some room. So is big D present? What do you guys think? I know you're all saying no. Okay. So we're going to start off with little d. Now we have a 1 prime. Which letter comes first in the alphabet, C or E? It's C. So remember, the 1 or the 1 prime means, okay, we have a big C, and we fill in with small case e. Okay? R2 prime, little r. Once again, there's no big D. Is there going to be a big C? No. There's going to be a big E. That's what the 2 means. And little ry, okay, means little d, and both big C and big E are there. Okay. All right, I know it looks a little messy, but it's coming up on another slide. So once you get the pattern and the code, so to speak, what everything matches with, it's really not hard. And you might say, well, why do we have to do this? You're going to see why in a couple minutes. Okay, it does make life easier when you're able to do this. All right, so now I'm going to clear my drawings. All right. This chart basically is table 6.2 in our textbook, and it basically outlines everything I just did with you. So you don't have to look at my crazy, horrible writing using Zoom, okay? And you could cover this up, and I guarantee you I'll get it right every time. This is big D, little c, little e, big D, big C, little e, big D, big E, and little c, okay? And then big D, big C, big E. And you can see the order is different, okay? So trust me, once you get what everything means, it's not going to be so difficult. And this is just another way of expressing what we did on the last slide. So big R means big D, little r, no big D. Okay, and then 1 and prime is big C, 2 is double prime and big E, O means little c and little e, Z or Y is both. Okay, and so I don't even really use the 0, I just use the other ones, and then I just fill in with small case letters. Okay, so the example here, big R2, the big R means we have D, the 2 means we have big E, we fill in with a little c. Okay, so just fill in with the lowercase letters when you need to. Okay, so we're going to talk a little bit about Rosenfield terminology next. I don't find this one to be used as often, but we are going to just briefly go over it. This basically tells us phenotype information that's useful when we're doing computerized data entry. And so the antigens are designated by a number. So RH1 this is similar to the international thing we looked at previously. So 1 is big D, 2 is big C. They do all the capital ones first, and then little c and little e. And so with Rosenfield terminology, if somebody had big D, they would write RH1 to indicate that the big D is there. If they had big C, they would write 2. If there was no big E, they would write -3. You know, the little c antigen would be having the 4 there, and the little e would be having the 5. It's not so bad once you get the hang of it. We're not going to concentrate as much on that one. So we already talked about the ISBT terminology. We looked at this on a previous slide. But just to review, it's the International Society of Blood Transfusion, and it's a way to standardize nomenclature throughout the world. So each antigen has a 6-digit number, and the first 3 numbers refer to the blood group system. And so we looked previously about how 004 applies to the RH blood group system. The other numbers refer to the Rosenfield system. Okay, so the ISBT number for the big C antigen would be 004-002. If it was the D antigen, it would be 004-001. Okay, so you can see how they are related. Okay. So when we're doing testing in the lab, how do we determine which RH antigens an individual has on their red cells? And you all know from, our virtual labs and talking about big D before, that we actually have an anti-serum against big D, anti-D. And that's what tells us the RH type, okay? Well, similarly, we have antisera that are directed against the other antigens of the RH system. So there's an anti-big C, okay? And the idea here, this testing would be done exactly the same way that you would do your forward typing with ABO and D, okay? So we'd have a tube for each antisera. We would label them, okay? And so it's 1 drop of the antiserum into its corresponding tube, okay? And then 1 drop of the patient's 3 to 5% red cell suspensions, and we do immediate spin. we centrifuge and reread. Now these reactions can be weaker. So sometimes they're going to be 1+ or 2+. They're not always going to be a 4+ like the ABO and D reactions. But when we get agglutination, it basically means that this person has that antigen on their red cells, okay? So basically, this is antibody against big C. We have antibody against little c, antibody against little e, and antibody against big E. And so we could test all of these to find out. We call that phenotyping, okay? So phenotyping, you know, to see which antigens a person has, okay? And similar rules. So when the red cells agglutinate, it means the antigen that corresponds to the antiserum in that tube is there. And so we call that phenotyping. Can't say it enough. So basically, I'm very sad about this, but when we would have lab in person, we would give you all the opportunity to have a partner draw your blood, and you could phenotype yourself to find out, you know, beyond your ABO and RH type, which RH antigens and antigens of other blood group systems you happen to have on your red cells. And maybe sometime in the future we'll have an opportunity to do that. I certainly hope so. Okay, so phenotype, remember, it's the physical expression. It's what we're seeing when we're doing our testing. The genotype, however, is the genetic makeup, and we can predict this by looking at the phenotype an individual has, and also by considering the race of the individual. And so we'll look at some data on this in a moment. This is not as clear cut, maybe, you know, in 2000 as maybe it was in the 1940s or what have you, when, you know, Fisher, Race, and Wiener and all of those people were doing their research, because these days we have many people that are multiracial. And so, you know, that kind of doesn't always follow through in every case. So ultimately, only family studies can, or molecular testing can determine the true genotype, okay? So when we're trying to guess a genotype or predict, we could look at charts based on race, but that's not always going to work today. But we'll practice doing it anyway. Okay, so here we'll look at some examples. So genotypes can be predicted if we have a person who's a pure race and we know the race of that individual. So our textbook lists Caucasians and blacks. And so, for instance, you know, if you are Caucasian, inheriting big R1, little r, big R2, and big R0. These are the most common genotypes that are inherited. And remember, you're going to have two. Everybody has two, one from mom and one from dad. If, however, you happen to be black, you could see that the prevalence is somewhat different. So same ones are there, but in blacks, the R0 is more common, followed by little r and then big R1 and big R2. Among both races here, little r prime, little r double prime, big RZ, and little ry are rarely encountered. So these are very uncommon genotypes. And this is a table from our book, Table 6.4, which actually bears out what I just mentioned to you on the previous slide. And so this is basically based on research data. And so, you know, we could see, you know, individuals that are white. This is the highest frequency. If you're black, it's this one. In both, little r happens to be second. Then we see R2 versus R1 and R0 versus R2. So how would this information, how could we predict, based on our phenotypic testing, the genotype of an individual? Well, firstly, we need to have this chart, okay, because, you know, we can't memorize, you know, the data or the research that's out there. And we're going to do this example two ways. We're going to do it if we have a person who's white versus if we have a person who's black, and we're going to see that the most likely genotype is going to be different, okay, because we have different data based on race. Okay, So in our phenotypic example here from testing, our patient's red cells agglutinated with anti-D, so they have D. Their red cells also agglutinated with anti-big C, which means they have big C antigen. They were negative with anti-E, so they don't have that one. They agglutinated with little c, and they agglutinated with anti-little e, okay? So, and you can see, remember, these are codominant, so it's entirely possible to have all 5, okay? Our patient in this case has 4 out of the 5. So we're going to predict the most likely genotype. And so basically what we do, okay, let's say our, I'm just going to go from left to right, okay? Let's say our patient is white, okay? So we want to look to the first genotype here, R1, that's the highest, most popular one inherited. And we want to see if the antigens that are present in big R1 fulfill, you know, what we got in our testing. Okay, so we got big D. Okay, the big D is there. Okay, that's good. So here's what I do as I go. I'm going to cross off. Okay, so it can cross off big D. Okay, now we need to have big C there. Okay, up, there it is. Okay, so this one fulfills big C. Okay, there's no big E, so we don't have to worry about that one. And then they have little e. There it is, little e. Okay, so we're able to get the D, the big C, and the little e from this genotype. So it's highly likely, okay, if we had a white person, since this is the one that is most frequent in the population, that they are R1. Okay. Now, remember, they inherit a set of other alleles from their other parents, so we need to fill in. And so what we're specifically looking for is we need a little c here, okay? So we go down to the next highest, which happens to be little c and little e, okay? And we can see, okay, there's the little c I need. And the little e is good because they have little e, so it's not adding something that, you know, was negative. And so we could say, okay, in a white person, the most likely genotype would be big R1, little r, based on our charts of frequencies. Okay? Now, let me go and do a different color. It's a pretty color that's going to stand out, let me think. Go for this one. Okay. Let's do the example of our patient being black. Okay. So we have the same results of testing, and I'm going to use a different color to eliminate. Okay. So in the black population, R0 is most prevalent. So let's see if this fits our testing. Okay. So we need big D, okay, that's fulfilled. We need little c, that's fulfilled. And we need little e, that's fulfilled there. Okay. So when we have someone who's black, they're going to be RO, because that is the most common inherited genotype in the black population. Okay, so we've eliminated big D, little c, and little e. What we need to find in our next genotype to provide the big C, okay, because we had a positive here with big C testing that wasn't provided, okay, by RO. So we go on down next to the second one, little c, little e. Now, looking at this, you know, at first you might say, oh yeah, that fits. And it does fit because it's, you know, we have a little c and we have a little e. However, that is not going to work because it's not providing us with the missing big C. Okay, so the other, you know, haplotype that this individual inherited has to provide us with big C. Okay? So we have to skip over this one. Even though it fits here, it's not giving us the missing big C. So we're going to go on down to the next one. And there it is, big C. Okay? So we can see this big R1 will provide us with big C, but before we jump the gun and say, oh, that's the one, let's make sure it's not giving us something we don't want. Okay, so big C is here, good. Big D is here, good. Little e is there, good. So that means that checks. So that's going to be big R1. Okay, and it's based on frequency. So we just go on down the road till we find the ones that fit. Now I want to point something out to you guys. Let's say we decided we wanted to look at this one, big R2. Okay. You can see, okay, the little c, the big D. However, what do you guys think? Is that going to work? No. Okay, our patient does not have big E, so this one would not work either. Okay, so hopefully that makes sense. So just remember, we look at our phenotypic testing. We want to start with the highest frequency haplotype and see if it fits. And if it does, cross off what it eliminates, and then go down to the next highest one and see if it provides what we need. And if it doesn't, as in the case here, we have to go on to the third one. And, maybe sometimes you have to go on to the fourth one. Okay? So, but you can see clearly here how, based on people that are of a pure race, we have different most common genotypes. Okay, I'm going to move on. I'm going to erase. I should have just cleared it. It's much easier. Okay, I'm learning. Okay, so what I'd like to do with this one is I would like you guys to help me. Let's do a different color. Okay. I want you guys to help me convert, okay, to the Wiener classification. And so this is really what we did on the last page, but you can't practice with this enough. Okay, so when we look at the first haplotype, big D means I'm going to write what? Big R. Okay, there is a big C and a little e. So there's only one. The C goes with a 1, so this is going to be R1. When we look at the second one here, we see there is no big D, and they've just decided to just not write it. So that means we're going to have little r. And there are only small case letters, little c, little e, so this just it's a plain little r. There's no 0 that goes with it. Okay? Let's look here. All right, our first haplotype, we have big D, which means we're going to write R. We do not have a capital C or a capital E, so think big D is the only capital, so that's a 0. Then we look at our second, excuse me, haplotype. We see big D, which means we write big R. We have the capital C, which is a 1, and there's no big E, so it's going to stay as that. And you can go back and double check me, and I guarantee you I'm right. How's that for confidence? If I got it wrong, then I'd be completely embarrassed. Okay, let me clear my drawings. Okay, and we'll move on. You can't practice enough. It's kind of fun once you get the hang of it. So this slide, we're looking at table 6.5, which is showing us Rh phenotypes and genotypes. This is a very exhaustive amount of data. But what's nice about it is it shows you the results of the testing. And so I think this is the one we did, right? This is the one we did. and you can go back and check. Okay, excuse me. But when you go on down, you can see, okay, in the second example, one thing I forgot to tell you guys is we talked about already how it is entirely possible to have all 5 of these antigens. And if you look at this row here, you see they have all 5 because they're codominant. Okay, but here is what I'm going to tell you. It is entirely, extremely rare not to have at least one type of C or one type of E. So what that means is if a person does not have big C, they usually have the little c, and vice versa. If a haplotype does not have big E, it should have little e. And so if you go back and you see how we filled things in, it bears out, okay? It would be extremely rare, okay? If you look here, you're not going to see any example where there are no type of C or E, okay? So even here, okay, this is a very common phenotype in individuals who are Rh negative. You can see they have little c and little e. Okay, you have to have at least one type of C or E. Okay, let me look for another example. Okay, for instance, here, this person doesn't have the big C, but they have the little c. Okay, so have to have at least one kind of C and one kind of E. Very unusual not to. And so this is basically the testing with the anti-sera, and then this is based on data, most likely genotypes, based on two races only. All right, so here we're going to look at an example of inheritance of Rh haplotypes. And when you look at this with me, you're going to say, now I understand why we need Wiener. Can you imagine if we were going to do this Punnett square, if we didn't have Wiener terminology, I would be writing out big C, big D, little e, and putting that in my chart with big D, little c, little e. It would be crazy with all these C's and D's and very confusing. So the fact that we have Wiener classification makes it much easier to fill out a Punnett square. Okay, so let's look at this one. So when you see a Punnett square with a circle, that indicates the mother. And when you see the square, guys are square. No, I'm only kidding. That's the dad. Okay? So we have an R1, R2 mother who came together with an R0, little r dad. And so we can see the offspring that they have. Okay? Or the possible offspring they could have, I should say. So let's look carefully at this. We see how the Punnett square is much easier using Wiener. So here we have the mother, big R1, big R2, and then on the side we have the father, big R0 and little r. And we're just going to do this Punnett square in the same way that we would for ABO. So I bring down big R1 with big R0, big R2 with big R0, big R1 with little r, and big R2 with little r. And so when you look at this, you can say, wow, like each one of these is completely different, okay? But what we can look at here, okay, for instance, the fact that each one of these parents has at least one big R, anybody know what that means? I wish I could see you. It means they're both Rh positive, right? So having at least one big R, they're both Rh positive. Okay? And when we look at the combinations of their offspring, we could say, okay, well, what percent of their possible offspring are Rh positive? Well, this one certainly is. This one certainly is. This one certainly is. Remember, because you know, having at least one R means you have big D, Rh positive. So it's 100%. Boy, that writing looks bad. So there's 100% chance of them having an Rh positive individual. Okay, which means 0% chance of Rh negative. Let me put on my drawings. Okay, hopefully that makes sense. Chat me or get on our discussion board if it doesn't, and I'd be happy to explain. Okay. So we could use our Punnett square simply for predicting Rh only as well, and that's what's being done here. So in this instance, we have a D negative, Rh negative mom. When someone's Rh negative, we write them as little d, little d. Remember, that means they do not have any big D, and so we see her on this side. We have an Rh positive dad who we happen to know. Remember, to be Rh positive, you could be big D, or big D, little d, but we happen to know somehow that he is big D and little d. So he's heterozygous for D. So we're going to do our Punnett square in the same way. D comes down, little d and little d, big D and little d, little d and little d. And lo and behold, what do we think? What is the chance of an Rh negative offspring in this case? Anybody? %50. Okay, so there's a 50% chance of Rh positive or Rh negative. Okay. I would love to do the example of my parents. Maybe I will. I have to make a new slide to do it. I think I will because it's just a very interesting one. Let's see where we are next. Okay. So I'm going to do an example of my family. I'm going to end the show. And I'm going to make a new slide here. I'm just going to type it. If my mouse works. Okay, there it is. Oh, I should have erased my drawings. Okay. I'm going to type. It's easier to type. Okay, so in my family, my mom was D, and my dad was also DD. And I know this after the fact, okay? So let's look at how I know it. Let me insert a table. Okay. I don't like the colors, but we'll deal with it. Okay, so how do I know this? So here's my dad is D, and D. And my mom is D, and D. Oh, where is that? D. Okay. I'm going to tell you how I know it in a minute. I know this after the fact, but I'll explain why. Okay. So in this case, what's going to come down? A big D from each. It's going to come down here, big D and little d. It's going to come down here, big D and little d. And what's going to come down here, little d, little d. So when we look at this example, we can say, and I knew that both my parents were Rh positive, okay, but guess what? I'm Rh negative, and guess what? My only sibling, my sister, is Rh negative too. So even though there was a 25% chance, I guess with each pregnancy, of having an Rh negative child, my sister and I hit the jackpot both times. So since we're both Rh negative, I can deduce that this is the only way my parents, what their genotype had to be, because if either one of them was big D, there would be no chance of Rh negative offspring. Okay, and here as we see, only 25% chance. So 75% chance of having an Rh positive child, only 25% chance of having Rh negative. Me and my sister both hit the jackpot, and I will say I also passed that negative RH jackpot onto my daughter, who happens to be RH negative too. So you just never know. It's interesting, and we'll talk more about that a little bit later. Okay, so I'm going to go back to slideshow if I can find it. Okay, so let's talk a little bit more about the big D antigen. The big D antigen is the most, we could say, antigenic or immunogenic in the RH system. What the heck does that mean? It means the big D antigen is very good at stimulating someone to make an antibody against it if an individual is exposed to it who is D negative. Okay? So what that means is, I already told you guys, I'm RH negative. If I were given red cells that had the D antigen on them, there's a very strong chance that my body would recognize that D antigen as foreign, and I would be stimulated to make anti-D. Okay, so that's what it means. Very, very immunogenic. So because of this, we really want to try to give D negative individuals D negative blood. So RH negative individuals, we really want to give them only RH negative blood or red cells. Okay, because if an RH negative individual who lacks D gets a transfusion of D positive blood or red cells, they could be stimulated to make anti-D. And so I just want to state, because I haven't said this previously, antibodies to antigens of the RH system are not like antibodies of the ABO system. So when we learned about ABO antibodies, we said they are naturally occurring. Not so with RH antibodies, and not so with most antibodies of other systems we're going to learn about a little later. So what that means is, we don't have, Landsteiner's rule doesn't apply. Okay, so I'm RH negative. I don't have anti-D unless I'm given a transfusion of D positive red cells and my body is stimulated to make that anti-D. Okay, so try to remember that. That's very important. Okay, and so here we see an example based on Wiener classifications of genotypes that have the most D antigens. And so we see here big R2 happens to have the most, followed by big R1, and then, I think I could understand why these are less, because, this little R means that haplotype lacks the big D, okay? So these are the two that have the most of D antigens. I am just going to say one more thing about giving RH negative individuals RH positive blood or red cells. Sometimes in emergency situations, this may have to happen, okay? And if we give an RH negative person RH positive red cells, we are not necessarily going to kill them as would happen when we, in the case of ABO, when we give an incompatible blood type and individuals die within a few minutes, okay? So why is that? Remember, ABO antibodies are naturally occurring. So if we have a type O individual, they have naturally occurring anti-A and anti-B. If we accidentally give them type A, the anti-A in that recipient's bloodstream is going to attack the A antigen on the donor cells, and it's going to cause a massive transfusion reaction. Okay. When we have a case of an RH negative individual, remember, RH antibodies are not naturally occurring. So the first time an individual may be transfused with D positive red cells, there's not going to be any harm. They might be stimulated to make anti-D, okay, but it's not going to cause any kind of problem the first time it happens. Now, if they make the anti-D and then they get a subsequent transfusion months later with D positive red cells, then there could be a transfusion reaction, okay? But we will learn in another unit that there is something called RhoGAM, which is a shot that we give individuals who are Rh negative to prevent them from making anti-D. Okay, and so it's given a lot to Rh negative pregnant women. We'll learn about when and why. But if we had to give, let's say, any individual, let's say we have a 70-year-old male in the emergency room and we have to give him O positive and he's Rh negative. We could also give him a shot of RhoGAM to trick his body into not making anti-D. Okay, so that is a wonderful, wonderful thing that we'll learn more about later. Just introduce it a little bit. Okay, so this next slide, we're going to talk a little bit about expression of D antigen. And there are some individuals that they're Rh positive, they have the D antigen, but they have a weaker expression of the antigen on their red cells. And what that means is their red cells may not test positive when we do our initial forward typing. Okay, so by now everybody knows forward typing, anti-A, anti-B, anti-D, and usually D positive people are going to have a pretty strong reaction on that forward typing. Individuals with weak D initially look like they are Rh negative when we do that forward typing, and we need to do another step in our testing, the indirect antiglobulin test, which we learned about in lectures 2 and 3. And the indirect antiglobulin test actually helps us detect these weaker reactions that may initially have looked negative. Okay? Newer monoclonal reagents that are on the market have enhanced the detection of weak D antigens without doing the indirect antiglobulin test. But we're going to talk about this indirect antiglobulin test anyway, because it's important for you guys to understand it. Okay, so with the weak D test, we sometimes will run Rh control as well. And so we talked about this Rh control a while ago, and now's the time where we're going to talk about it again. Okay, so let's look at sample number 1. So this patient's red cells were positive with anti-D. They did not react with the Rh control. And so remember, when we were talking about reagents, I mentioned to you guys that whenever we have anti-sera, it's not 100% pure antibody. It's diluted with something. And the diluent most often used is albumin, which is a protein. And so sometimes people can react with the diluent alone. So the Rh control here is simply the diluent, the albumin, the 20% albumin or whatever, that is used to suspend the anti-D in. So this is ideal, what we want to see here. The patient reacted with anti-D. They did not react with the Rh control. And so we could interpret this as someone who is Rh positive. They have the D. When we have someone here not reacting with anti-D and not reacting with the Rh control, they're initially looking like they're Rh negative. This is a time when we would want to run the indirect antiglobulin test on this person to completely make sure that they don't have, okay, they don't have the D, or maybe they have weak D. Okay, so we'd want to do more testing on someone like that, okay, that tests negative initially. When we have an individual who's reacting with anti-D and also reacting with the reagent control, this looks like cross-reactivity, and so we really don't know if they're Rh positive or not. We're unable to interpret this because they're reacting with the albumin that's used as the diluent, okay? So we may want to try this with a different reagent that is a low protein reagent to try to eliminate that reactivity. Okay, so let's talk a little bit about how someone inherits the weak D antigen. So studies have shown, research has shown that it actually is more common in blacks, and it's due to inheritance of a weaker form of the D antigen, often due to little c, big D, little e haplotype. All right, let's think about this. Let's convert it to Wiener, and it's going to look familiar. I'm getting on your nerves. So big D means R. Everything else is small, R0. Okay. Do you guys remember before how when we were looking at frequencies of haplotypes, how R0 is, I think, the most common one, okay, if you're Black, and so hence, you know, inheriting this haplotype is more common, you know, in the Black population, and it happens to lead to weaker expression of the D antigen. So with weak D, as mentioned previously, we usually need to use the indirect antiglobulin test to detect the weak antigen, because initially it looks negative on our forward typing. And so we're going to look at how the weak D test is done in a few minutes. If we do detect the weakened form of the antigen, these patients would still be considered Rh positive, and they're still able to receive D positive blood. Okay, they just happen to have weaker expression. Clear my drawings. That's my thing, clear drawings. There, okay. So this is actually a good picture from our book that's going to explain it. So the weak D antigen is related to position effect of how alleles are inherited. The D antigen may appear weak when the C antigen is inherited trans to D. Okay, here we go. Hopefully you remember cis and trans. Cis is when they're on the same chromosome. Trans is when they're inherited on different chromosomes. So here we see a big C on the chromosome from one parent, which is trans, to the big D they got from another parent. And so this could lead to weaker expression of D antigen because they're inherited on separate chromosomes, from separate chromosomes. Big C little e, which is R prime gene, is paired with either big C big D little e R1 or little c big D little e RO. And so just remember, these patients are considered weak D positive, and they're able to receive Rh positive blood and red cells. So here's our weak D test procedure. It's actually kind of fun to do. Well, students don't usually think it's fun to do. So we're going to have our two test tubes. One is anti-D, the other one is our Rh control. And so we add 1 drop of anti-D to the D tube and 1 drop of the Rh control to its tube. And then we're going to add 1 drop of the patient's 2 to 5% red cell suspension into each. Instead of centrifuging and reading immediately, we are not going to do that, okay? And that is described here. So instead of centrifuging right away, this is showing, okay, how we added the reagent. We're going to incubate instead at 37 degrees for 15 to 30 minutes. So we basically take these tubes and we put them in our heating block for 15 to 30 minutes. After that incubation time is up, and remember, you know, sometimes that incubation time allows antigen and antibody to come together. Remember the first stage, sensitization, okay, it's allowing more time for that. Instead of centrifuging and reading, we are not going to do that. We're going to wash each tube 3 times with saline, and thank goodness for cell washers. So when we finally see each other again, you guys will have a chance to use a cell washer, and it's nice. It kind of looks like a centrifuge, but it actually pumps saline into, it has a rotor like a centrifuge. It can hold 12 tubes, and it pumps the physiologic saline in there and washes the tubes, centrifuges them, gets rid of the wash, and then, you know, so you can program it to how many washes you want to do. So we really need to wash 3 times with saline, and this is a good review of our antiglobulin testing. So I hope you remember from lectures 2 and 3 when we talked about the antiglobulin test that it's critical to always wash away any unbound proteins or complement before we add any kind of antiglobulin reagent. Failure to do so, if we have some proteins like unbound antibodies lingering in those tubes, they can neutralize our AHG. And maybe you remember neutralization, false negative reaction, okay? So we wash 3 times, then we're going to add 1 or 2 drops of our anti-human globulin reagent, our anti-IgG. We're going to centrifuge for 15 seconds and read it, and this could be some very weak reactions. If we get a positive here after adding our anti-IgG, we would grade it 1+, 2+, what have you. That means this individual has weak D. So we just needed this anti-human globulin to help us detect it. If, however, we get negative with our anti-human globulin, we're not done. We're going to add a drop of check cells, which are our IgG-coded cells, to our negative results. Spin and read. Remember, check cells should always be positive. It's confirming that we did indeed add our AH gene, it was functioning, but what it means for the patient in that case would be negative, no weak D, truly RH negative. Okay. Okay, so next we're going to talk about weak D, but this is different. This isn't weakened expression of the antigen due to cis or trans. This is because, or this happens when individuals have partial D antigen. So these individuals are still considered D positive, but they happen to be missing certain pieces of the D antigen, and so hence the name partial D. When they are exposed to the whole D antigen, let's say they get a transfusion of D positive red cells from another individual, they can actually make anti-D that's directed against the missing pieces of the D antigen that they lack. Okay, so it's actually pretty interesting. Partial D antigen would be detected on our forward typing. It reacts strongly with monoclonal reagents. When are we going to suspect partial D? When we have a person who types as RH or D positive, but they also have anti-D, and the anti-D that is present in their serum or plasma does not react with their own red cells, which is our patient control. So the patient control is negative. And remember, patient control is when we take the patient's 3 to 5% red cells and combine it separately with serum and plasma from them, and we get negative reaction. Okay, so the anti-D that they have does not react with their own cells. However, it reacts with other D positive cells, and that's a clue that they have partial D. This is also more prevalent in blacks. So what's the significance? The American Association of Blood Bank requires that all donor cells be tested for weak D antigen if they initially type as RH negative on forward typing. Okay? Now, here is some important stuff about this. All donor cells. So if you're working at the Red Cross or another blood donor center, they absolutely have to test each donor who initially looks like RH negative for weak D. Why? If we have a person who's weak D and we miss it, and we call that donor RH negative, their red cells could be given to an RH negative individual like me and stimulate me to make anti-D. Hopefully that makes sense, okay? Because they're really not RH negative, they do have D, okay? And so remember, D is very immunogenic, so even weakened expression of D could stimulate an RH negative recipient to make that antibody. Testing for weak D antigen on recipient samples is not required. So most hospital labs are not looking for that weak D antigen in the recipient, and that's the person who's getting the transfusion. Reason being, it's not such a big deal that way. Okay, so let's look at what would happen. Let's say we have a weak D person who's in need of a transfusion. We're not picking up their weak D on forward typing. So what does that mean? We're calling them RH negative. So that means they would get RH negative red cells. Not a big deal, because remember, RH negative red cells do not harm anyone. Okay, so missing it that way is not a big deal. Hopefully you see how this, however, would be really you know, more serious. And so I think that's where we're going to conclude this first part of lecture, okay, on the Rh blood group system. So I'm going to stop our recording, give you guys a chance to let all of this sink in a little bit, and we'll move forward with the rest of it in our next recording. Have a great day, everybody.